In order to come up with a viable mechanism for this process, we must consider the evidence on hand. The reaction is known to be reversible since alcohols react with halide acids to generate alkyl halides. Here, an excess of the water solvent ensures that the alcohol product is favored. Addition of more alkyl halide sees an increase in the reaction rate, however adding more water has no effect. Stereochemically, if a chiral substrate is used, an achiral mixture of enantiomers is formed as a racemic mixture. Further, the reaction gets faster as the substitution pattern changes, with tertiary substrates reacting fastest. Importantly, use of polar protic solvents gives the fastest reactions, with the solvent able to play several roles in the process. Putting the experimental evidence together, a viable reaction pathway will reveal itself. Firstly, since the reaction is reversible, it must be governed by the ideas of equilibrium and Le Chatelier's principle. Indeed, adding more water sends the reaction to the product side. In the rate experiments, adding more substrate results in a rate increase, while adding more water does not. This agrees with a unimolecular rate determining step. The stereochemical evidence, in which a chiral substrate delivers a racemic mixture of products, also matches a unimolecular process in which a flat intermediate species is formed. Additionally, increased reaction rates are observed with increased substitution at the alpha carbon, which would facilitate the formation of the carbocation intermediate. Lastly, polar aprotic solvents increase reaction rates, since they help the leaving group break off and also stabilize the intermediate formed. Now the question arises as to which mode of reactivity the evidence supports. A stepwise process through an intermediate, or a concerted process in which everything happens at once. The stepwise pathway, in which the leaving group breaks off first, agrees with all of the evidence, including the unimolecular rate determining step and the stereochemical outcome. The concerted pathway does not match the evidence because the rate determining step would be bimolecular, and that reaction should result in only a stereochemically inverted outcome. Now that a stepwise pathway with a unimolecular rate determining step has been established, we need curved arrows to describe how the bond breaking and bond forming events occur. Loss of leaving group matches the slow, rate determining step, in which the halide breaking away is facilitated by the polar protic solvent. Since the halide is more electronegative than the alpha carbon, the halide takes the bonding electron pair, leaving the carbon with a positive charge. The carbocation is stabilized by additional alkyl groups being attached through hyperconjugation, and the carbon electrophile will now be sp2 hybridized and flat. Solvent is then able to act as a nucleophile and attack the carbocation from either side. This step will be fast and, when a chiral starting material is used, result in a racemic mixture of enantiomeric products. All of this may be summarized by two mechanism arrows. The first shows the leaving group breaking away, and the second shows the nucleophile attaching. The oxonium product then transfers its extra proton to solvent, and the alcohol product is realized. The stepwise pathway matches all of the available evidence, and the solvolysis process may be described by two mechanism arrows. Loss of the leaving group agrees with the unimolecular rate determining step and formation of a carbocation intermediate. If that intermediate is flat and prochiral, then a racemic mixture would result, as the nucleophile may attack equally from either side. The reaction goes faster as the number of substituents attached increases, as the carbocations become more stable, as do the transition states leading to them. Those transition state energies are also lowered by the polar protic solvent facilitating the leaving group breaking off from the substrate. As such, all of the accumulated data leads to the SN1 pathway shown.